Okay, so I have marked or sent back most of the second titration, so your methods are pretty good. There's just a couple of little things that please remember for the iron tablet. Every time you make a rinse, you make a change or you add it, or every time you make a transfer, you make a rinse, because you don't know how they're going to set up their mark scheme. And there's a few of you for the ending of the maths, it just still needs a tiny little bit of work. So you need to recognize that you have grams per litre and you've made a solution that is grams per 250, and that's going to be equivalent to a certain number of tablets. So you need to be able to do that conversion downwards. But for the most part, it's really good. So well done you. Just the last thing, because I don't think it's expressly said, and in page 123 is, do you have a space? So you just need to recognize that KMNO4, before we ever use it in a titration, you always have to standardize it, and it's why that is. So there's room in my version, but I don't know if there's room in yours at around page 123. So you just need to include that KMNO4, it will decompose no, we got some people that are missing. It will decompose, so it literally falls apart by light or heat. So that's all stored in brown bottles to protect it. And for certain things that we do, even in sixth form, if I make it too early, it actually goes that brown colour, it'll go to Mn4+. Okay, so can we get miles in? And the other little thing that we want is that it also reacts with water. And there's obviously water in the solution that we're making up. Okay. And once you're ready there, then it's roughly page 136 of our book. So unless you now have any questions on iron KMNO4. Okay. So the one we are looking at today is an iodine thiosulfate titration. And if you're really lucky, will be the only two things that are going to be in your question. But there are issues in making iodine in solution. Because iodine is singly bonded, because it's got the exact same element in it, it is non-polar. So how do we get something that's non-polar to actually dissolve in water? So there's a couple of ways that you can actually make iodine in solution. And yeah, I have to tell you how all the different methods. So sodium thiosulfate is complex ion, so Na2S2O3. You will see it in the formulas. It will always nearly be given as S2O3 2- in the formula or in the equation, sorry, but you have to know or recognize this part in the question for calculating molar mass. So this is always going to be written in bold. Can't spell this morning. For molar masses, so just remind yourself of that. Why are you now not playing ball? Okay, so you don't have to draw the structure, but it is a complex ion with the 2 negative overall charge. Now, can you work out what the oxidation states of things are? So what is the oxidation state of S? So what do we think? Any takers?
+2.
+2. So we have Na2S2O3. Oxygen is -2. 3 of them -6. Makes everything over here +6. Sodium, because it's group 1, is going to be +1. 2 of them +2. So both of these together are +4. It makes each one +2. Yeah, it's already done. Okay, so in terms of sodium thiosulfate, it is a reducing agent, so it is itself going to be oxidized. It is this proper, really, really big fat crystals when we get to weigh it out, which is great. It makes it really easy for weighing it out. It is not a primary standard because it has this water of crystallization attached. So therefore it will have to be standardized. And it will react with iodine. Ooh. So this photo, the picture doesn't really do justice to how big the crystals are. They're kind of like Tic Tacs. Okay, so it's going to react with iodine, and this is our equation. So this is one of the ones that you can do without oxidation states, because you deal in half a change. So do you want to balance that for me? So you don't need oxidation numbers for this one, but if you do, you'll be dealing with a half electron for the change between sulfur on the left and sulfur on the right. So this one is as simple as balancing your eyes and putting a 2 across here. So if it's a really good day and she gives this titration, this will be the only equation that will be there, and it'll be very straightforward in terms of its maths and all of the different bits. Okay. Now,
Miss, where it says underneath formula of crystals, note this is not a, what are we supposed to put in there?
it's not a primary standard because it has that 5H2O in it. Straight away that makes it can't be a primary standard, because if it's a really hot lab, there's going to be less water attached. If it's a really cold lab, there'll be more water attached because the water vapor, the water crystallization will evaporate. Okay, so sodium thiosulfate isn't a primary standard. It has to be titrated against a standard iodine solution. Okay, but this is the issue. So we'll come back to the titration, or you've done the balancing. So we can't make it by direct weighing, and if we were in school I would show you why. So you had this words when you did states of matter when you were little first years. So iodine sublimes, what does that mean? It's a really nice word, sublime, but what does it mean? Any takers? So I have a version of this in school. It's done with test tubes though, and you just have your iodine in there and you crystallize it or you heat it, and it'll go from solid to gas. It bypasses the liquid phase. So that can be an issue if you're trying to weigh something out at room temperature, because all the time it's making iodine gas. So it'll go directly from a solid to a gas is one issue, and then the other issue is it's not soluble in water because it's nonpolar, covalent bonding. So how am I supposed to make a standard solution of something that I can't weigh out and something I can't dissolve in water? Okay, Sarah, I'm going off you. Okay, so that we've said, if you where I've written for you method 1, if you just want to put an asterisk, she will give iodine thiosulfate Na2S2O3 straightforward. So she just tells you in your question you have this concentration of iodine, this tighter volume of sodium thiosulfate. You have a ratio. It's dead straight. It's straightforward. There's nothing weird or wonderful. And she's giving you that, but she's not telling you anything about how she made the iodine, because she's being nice. But there's 2 ways that you can make iodine in a conical flask. So what you would do is you would actually put KMnO4 and Ki in your conical flask. So this would go into your conical flask, and the 2 of these together would react and you would liberate iodine. And then the second thing you would do is you would titrate what's in your flask with your thiosulfate. So these are what are called indirect methods to make your iodine. Now, again.
Where does that go?
So in mine I have method 1, standard solution of acidified KMnO4 with excess Ki. So this is going in your blurb. Have I written this wrong for you? Okay, let's go out and I'll write and I'll match yours. No, I want this all together. Okay, I'll match it to yours. Okay, so for method 1, you're going to react a standard solution of acidified KMnO4 with excess Ki in your conical flask. I'm going to say titration flask so you'll get your head around that we would do this as we're setting up our titration. So it's kind of one of the steps that we do it. So this would be in the flask, this is the equation. So you have it here, I minus plus MnO4 minus plus H plus goes to I2 plus Mn2 plus H2O. Do you want to balance this for practice? Or do you want me to just write the answer? I do not mind.
Write the answer.
Okay, it is a Monday morning. So it is going to turn out to be 10I minus plus 2MnO4 minus plus 16H plus when you get there goes to 2Mn2 plus 5I2 plus 8H2O. So you have in your flask liberated iodine is the words they use to describe this. So this is liberated. Means it's made, it's released, it's in your flask. Just in terms of oxidation and reduction, this is going from -1 to 0. So that is an increase in oxidation number. This is being oxidized. This is going from +7 to +2. It is a decrease in oxidation number. This is being reduced. Now, the KMnO4, so we go back to stoichiometry language, is limiting. So that means there is a fixed amount of it and we know exactly how much is there. And because we know the amount used, we can then, if we had to do a piece of maths, we could calculate the amount of iodine made. So it's a limiting reagent. And we know the amount used. So that implies we know the amount of iodine made. So literally it's not quite a titration, but in your flask you've essentially done a piece of titration maths, or you can do a titration maths, because you'll have a volume of KMnO4, you'd have a concentration of KMnO4, and you would be able to work out how much iodine you made if you wanted to.
This is that first thing in the second equation, is that IO?
It is 10. There's 10 of these because you've got 10 over on this right side over here. So that should be 10I minus. Apologies. Good spot, Sarah.
Yeah.
Was that Sarah? I can only see one.
Jill.
I can only see one sister. You've turned off your camera, Jill. Okay, so I'm just going to go back to this. So this is what you'll have done in your flask. Whereas in terms of our titration in a second, this is the titration equation. And we'll come back to it in a second. So method 1 is we in our conical flask we're making iodine using KMnO4 and Ki. In our second one we'll come back to the ratios. So this was actually why I was matching yours. Okay, So we'll come back to this. So here's our second method then. So in our second method, this is going to be in your conical, in your titration flask. So we're doing all of this in our titration flask. She may put in a question the fact that we use potassium iodate, KiO3, again with excess Ki, and we liberate the iodine in there. So we're making the iodine in the titration flask before we've ever started our titration. And you can do it 3 ways. She's either telling you have the iodine, perfect. She's telling you added KMnO4 in there, okay. Or she's telling you now you've added KiO3 in there. So this is our balanced equation. This is going from +5 to 0. This is going from -1 to 0. So this is oxidized, and over here it is reduced. So irrespective of what she gives you to begin with, there will be iodine in a flask. We in school will use the KMnO4 method for making our iodine in our flask when we finally get to do this titration. Again, if we have excess Ki, all of the KiO3 is going to be used up. So that is the limiting reagent. You don't have as much of it. So it is limiting. Okay, so this is in the grey blacked out bit, and this is the important part for you, because we have said I2 is insoluble in water. So it doesn't matter how we're making it. The fact that we have now made iodine and we have this excess Ki present, what happens is it forms what's called I3-, or it forms triiodide ions. They act exactly like iodine, but the I3- is, for starters, more soluble than iodine in water, and it actually keeps the iodine that is made in solution. So that's a real important point. So if you need to draw for yourself, in your flask you will have I2, but in your flask you will have also I3-, and it's this I3- that acts like iodine, but it keeps the iodine in solution for you. So this part here is an answer to a very specific question. Whereas the stuff that we've done in terms of how to make the iodine, the relevance to that may have to do with how you would go about doing the maths. Okay, so The next grey box is down here. So in this particular one, we should use distilled water. Yeah.
Can you please go back for a second?
Yeah.
Okay, thank you.
Thank you. So in this, we should use distilled water instead of deionized, because there could be dissolved substances in our DI. So there could be chlorides in there or other things that will act as oxidizing agents. So they are going to they'll reduce our titer for us when we actually do titrate, because some of it will be gone. So if you're giving her an answer, we're using distilled because of dissolved substances, and you're giving her the example. Okay, it's not enough just to say this, or only if it's a really good day. Okay, so we'll have just a little look at the little titration diagram. I will now just talk about what that making the iodine in the flask means for us trying to do the maths. So this is our flask. So we'll have our thiosulfate is going to go in our burette. It's colourless solution. Down in our titration flask, we're going to have the KMnO4, the sulfuric acid, so the same protection, this whole Mn7 plus, we want it to be able to go to Mn2 plus, but we're doing this now in our flask, and we have the Ki, which is the stuff in excess. So by the time we're done, just
We can't see you. Wait,
speak louder, Mikey.
we can't see what you're doing.
I am sharing my screen. Can you see the?
Like up under the screen, like.
Okay, on.
Go down if you can.
So the same thing still apply as when we did the iron KMnO4. So the sulfuric acid here is to ensure that the Mn7 plus is going to go to Mn2 plus, and this Ki here is in excess, and that's the whole I3 minus. It's going to make I3 minus with iodine to keep the iodine in solution. So this is going to make iodine in the flask before we've ever titrated. And we get two equations with it. So this is the reaction in our flask, and this is the titration. And there is the two equations for it, and it's very possible that she will give you both equations. Now you need to be able to figure out your ratios. So we have said the 2MnO4 is being used to make us iodine. So the first ratio that we're interested in is 2MnO4 is to 5 iodine. In my second equation, how do I figure out how many thiosulfates that's equivalent to? So I've got to find the link between this and this. So how many thiosulfates is that? It is 10 because I need to make these two things comparable. So I have 5 iodine in my first equation, I'd have 5 in my second. That must mean I have 10 thiosulfates. So this is the ratio if she was to give you both equations, and I think our first question, or the one that I'm going to look at with you, is the not straightforward way. So that's the ratio. 2 is to 5 is to 10. And the reality is that she'll more than likely just give you this equation by itself. She won't make it difficult, but we have to be prepared in case she does. Okay. So we've said for the redox kind of their own indicators to a point. So the indicator that we use for this titration is iodine initially. So iodine, when we do this, it starts off at a kind of reddy brown and we go to a pale straw yellow. I call it that you would, it's like real healthy wee. If you're really hydrated, you get really pale yellow urine. This is what your iodine, you want it to go to that colour. And once it's at that colour, we add in some starch. And then your colour change will be the blue, black to colourless. So at our beginning, it's kind of brown. Towards the end point, it goes this beautiful pale yellow. We add the starch in at that point and it'll go the blue, black. And at your end point, it'll go colourless. Now, when we finally get to do this as a titration, once we add in our blue, black here, we are literally drops away from our end point. And it's really, really important, and we'll put this in at the bottom of underneath the table, that we have to add the iodine when it is this pale straw yellow. Because if you add it too soon, you never get to see your end point.
So when the solution goes pale yellow, then you add the
starch.
starch.
You add the starch, and you don't add it before that. So are we okay with that part? So there's lots of colour changes here, and obviously she will love to ask them. So brown to pale yellow, pale straw yellow it's called, to blue, black to colourless. And just our point, if you add it too early, it forms a complex. So starch is slightly, for want of a real basic way to describe it, it's kind of forms a kind of a cylinder, and the iodine will go inside the cylinder, and that's when you see the blue, black. But if you add it too early, then the iodine kind of gets trapped in here and you can't titrate it. So it forms a complex with your iodine and your end point won't be determined. Okay, it is 9:18. You are going to turn off your cameras for me until 9:25, and then I'm going to do one of the pieces of maths with you, and then I'm going to let you on your way. Okay, if you have any questions, please ask. If we were in school at this point, you would be weighing out your sodium thiosulfate doesn't really matter what mass you weigh out because it's not our primary standard. We'd make our 250 solution. We'd make our iodine solution in our titration flask. So we'd be adding 25 centimeters cubed with the pipette. We'd be adding 20 centimeters cubed of sulfuric, and we'd be adding 10 centimeters cubed of 0.5 Ki with the, again, a pipette. So we do our titrations, blah, blah, blah. We'd fill out our table. This is the question that you have. I think it's on page 139. So this didn't quite fill out here for me. I don't know why. 2I minus plus S4062 minus. So it's telling you you've 25 centimeters cubed of 0.2 molar potassium permanganate. So we're going to have to do something with that. We added our dilute sulfuric and our excess Ki, and the liberated iodine is titrated against sodium thiosulfate of unknown concentration. Our titer is 18.73, and it's then asking you to calculate the molarity of your sodium thiosulfate, and your question also asks you in your book to calculate the concentration of the sodium thiosulfate solution in grams of crystalline sodium thiosulfate. And I would just refer to that and say, please note how it is in bold. So when you're calculating a molar mass, this is the molar mass of what you want to calculate. So I'm just going to show you I'm going to do this one, or at least set it up for you. So you will, when you make your table, you will have three things in your...
Yes.
Yeah.
Yes.
Are we supposed to be able to see your screen?
Oh, crapola. Thank you, Jim. You are. Okay, I'm just going to go backwards to here. Okay, so in the question at the very bottom, this is in bold. For the SEC, if something is in bold, that is what you are using to calculate a molar mass. Okay, but we have two equations that have been given, and you need to find the relationship between the two equations. And in terms of your table now becomes this. So you will have your KMnO4, if you have three things in there, KMnO4, your iodine, and your, I don't know why this won't work for me. Yeah, it's on a go slow. This is why I don't usually like the whiteboard as opposed to my one. So I'm going to go back here because I prefer this. Or is it my internet now? So you're all still moving. Okay, we'll go try this one. So Na2S2O3. So you have to figure out what are the things that I'm going to need to be using in my titration, and this is going to tell you. So there's no mention in this of iodine, a concentration of iodine or a volume of iodine. So the numbers that I have are the 25 centimeters cubed. So we have the V, the M, which is a C, and we have our N. So I have the 25, I have 0.02 M, I have my titer value 18.7 centimeters cubed, and if I read down through my question, it's asking me to calculate the molarity of my sodium thiosulfate, so this is my question mark. The ratio I'm getting over the two equations, so in the first equation the ratio of KMnO4 to iodine is 2:5. In my second equation it's a 1:2 for iodine to thiosulfate, which is the equivalent of 5:10. Okay, so I can ignore that. I don't have any values for this, so in reality I don't need this at all unless they specifically mention moles of iodine at the end point. So I will be starting in here, as we always do with our maths, and I will then work out the thiosulfate side. Does that make sense? So you have to use the numbers that you're given. And kind of the big giveaway in the question will be the fact that there will be two equations in there. Usually that says you're going to start with KMnO4 and you are going to end up over with the thiosulfate. So the maths is now straightforward. There's no difference to what we've done before. The only difference is the setup of the table. So do you think you're happy with that? Is there any questions? No, I've got a couple of shakes of the head. So I'm going to give you the answer to the question on page 139 now and the 2007 on page 140. So for page 139,
It's go for the W.
Yeah.
So when going across, like for the ratio, would that be
2 is to 10 or 1 is to 5. Yeah, because
nothing to do with the I. Like,
say it again.
you don't do anything with the I too.
No, unless, so the only thing that this is really on a go slow. The only thing that they can ask, so on page 141 there's two questions, a question 9 and a question 10. In the question 10 you would have to use the ratio for KMnO4 to I 2 is to 5 to figure out how many moles at the end point, and then you'd go the 5 is to 10 iodine to thiosulfate. So the question 10 is the absolute maximum that she could ask you to do. But in this particular question, you don't need that part. But I really suggest that you put the three things into your table, and you will clearly see that there's nothing for iodine that you'll have to calculate. So page 139, I'll leave you with the answers. The molarity is 0.134 m, and the grams per litre is 33.1. And on page 140, and I'll attach the question 9 and question 10 answers as opposed to solutions to the assignment post. But for the 2007 maths, it is 0.125 m and it is 31.0 grams per litre. So the only thing I would say is most of you are getting your significant figures bang on. There's still a couple of people, for whatever weird reason, and it's only in like one part of one sum, you've done it right absolutely everywhere else. So just 3 significant figures if there are 3 significant figures in your answer. So up here, this is 1.8. That tells me I can have 3 significant figures in my answer. So try not to round up too soon. And just final answer is that. So I've given you the questions to do. There's 2 theory parts and there's some maths. And we have a single on Wednesday and we have a double on Friday. Now we only have one titration left, and it's the exact same titration as this, except we use bleach in our flask to make iodine. And I was thinking that if you're okay, I'll do whatever you want, it doesn't bother me, but that you take Wednesday to do all these pieces of maths, and that we go again on Friday. Does that seem like a better idea? So it's either a shake of the head or it's a nod of the head. Okay, got the ladies. So Mikey, if you want to come on Wednesday, I'll be here on Wednesday for you. Did you understand the question or the statement? So that you can have Wednesday to do your maths. I'll come online on Wednesday at lesson time, and if you have a question, you can come and ask. But as such, I don't need to see you. Is that okay? Okay, so you have the questions in the class notebook page. As I say, I'll put up the answers to 9 and 10, and the video link for this titration is in there. Have a look, see what Declan Kennedy says about it, and other than that, we will love you and leave you. Is that okay? Oh, you're giving me so much for Monday morning. All right, it is lovely to see you all. Be safe. I will come online on Wednesday during our lesson time if you have any questions. Otherwise, I shall see you on Friday.
Thanks, Miss.
Thank you.
Bye.
Thank you.